Okay, it's time. Welcome back. So I dropped a fairly big hammer in terms of convex optimization sums of squares last time, and we started to work with it and understand how it could be useful for Lyapunov functions. So my goal for today is to, well, at least show you how to use that same set of tools to do regions of attraction. That's going to be a big step forward, is the region of attraction version. But also, I just kind of want to play with the tool that we gave you a little bit more, step through a couple of examples carefully, and make sure that you understand what's happening. And I think you should be a little surprised at how well it works in some cases, and we'll try to also understand its limits. So as I've promised, I'll just try to give the big picture context again, and then recap and jump in. So the big picture from Lyapunov, the computational perspective of Lyapunov function was that we were going to go from this relatively hard constraint to satisfy of finding some function that was going downhill at exactly some rate, solving a big PDE, and we've relaxed that to now just say I'm going to find any function where if it goes downhill at all, then I can already say something interesting about the long-term behavior. And what we did last time is we started off by saying we could try to satisfy the first version, which I thought was hopefully easy to think about, was to say I'm going to pick a bunch of sample points xi and say for all I could evaluate and make sure that my function is less than 0. That was enough in the simple case of the pendulum. If I were to search for a Lyapunov function that was scaled appropriately and just satisfied this at a bunch of points, that was enough to reconstruct something that looked like the mechanical energy of the pendulum. But Sava asked, he says, but this isn't a certification of that condition. This only holds at a few sample points. How do you generalize it to all x? So the big new idea was the sums of squares version, well, even just the convex optimization version. Allowed us to say for all x, v of x was greater than 0 and v of x less than 0, v dot of x less than 0, right? This changed from some number of samples to really to say something could over all x was the big leap that we made last time. And we could see it already even in the simple linear systems case, where if I had, this was a really important example, even though it's sort of too simple for the long run, but I think it exercises a lot of the right machinery. If I have just a simple linear system and I want to find a p that's greater than 0, such that v dot, which I can write as x transpose p ax plus x transpose a transpose px. I put a note about that on Piazza, right, about that going from there to there. I want this to be less than 0. It turns out I could write that as a semi-definite program, right? Search for a p as a semi-definite program. Right, this is one semi-definite constraint, and then this other one in the middle also became a semi-definite constraint. And what's perhaps surprising is that optimizations that fit into the class of semi-definite programming are convex optimizations. They are something that if a solution exists, the solver is guaranteed to find one except for numerical limits or running out of memory or something like that. Okay? And I think another thing that's surprising is how well that example, which looks just like so stuck in linear systems, on the face of it, that just looks like, okay, well, that's only going to work for linear systems. How are you possibly going to extend that to nonlinear systems? What's amazing is that that extends beautifully to nonlinear systems, right? And the general form of that was to just go from this into the same sort of quadratic form, but with nonlinear basis functions on the other side. Instead of just x, we can generalize that to nonlinear basis functions. Okay, I'm going to say that again in a different way, but just to make sure we're happy. But that's the big leap that helps us go from it's, you know, in machine learning, you might call this the kernel trick, right? There's a lot of different ways to think about what this is doing, but it's just leveraging the power of quadratic forms. Okay. Everybody likes gradients and gradient descent or whatever, you know. Quadratics are like the next thing. It's going to be big. Okay, so let me say that a different way, just to sort of say it, right? So we've been saying, we talked even in the dynamic programming about the linear function approximators. Which we wrote as, had some function, alpha I, vi, right? Which I could write in matrix form. If this becomes a vector of this, right, I can write that as a dot product. And we're going to look, you know, these things are potentially hard. It's not obvious how to make this be greater than 0 or less than 0. So the reason that generalization is powerful is that I still have a new linear function approximator, but using this sums of squares version. Still linear. In the parameters, right? Which I wrote it first like this. But actually, the more general form is that form up there, to say, I'll use M again here, but just think of that as a more clever way to write this. Okay, it's a richer, it allows positive combinations of that, not just element by element wise, right? But this clearly, no matter what mx is, this thing is this quadratic form, if p is a positive definite matrix, then basically by definition this is always greater than or equal to 0. Right? It's a sum of squares. So this gives us a set of tools for searching over interesting functions that are positive, are only positive, or with a minus sign, only negative. And those are exactly what we needed to satisfy the Lyapunov conditions. And more generally, you could say this is a general tool for polynomial optimization. The immediate tool is if I want to say that p of x, p a polynomial, greater than equal to 0 for all x, then I can write that as in this form. I can say p of x equals, m transpose p mx. And then you remember I can do coefficient matching and then write that as an optimization problem. Hand it to a convex optimization solver. even more so, if P of x has, if we want to search over the coefficients of the polynomial, right? If this is like alpha 0 plus alpha 1 x plus alpha 2 x squared, right? If the coefficients of the polynomial are unknown, it turns out that coefficient matching still works. I get equations that are, the coefficient matching gives me equations that are linear in the decision variables, and turns out is still just adds linear equality constraints, and I can search over the polynomials. So I'm going to do that now. Like I said, this is a big thing I threw, but I want to make sure you see that in some details in a couple specific examples. Any questions at the high level? Yes? If we have, yes, if you want to have decision variables, which are the coefficients of the polynomial, then equations of this form can be written using a positive semi-definite constraint and linear constraints on those decision variables. So that's still in the scope of semi-definite programming. I hesitate to use the word symbolic, but just because that means a certain set of computational tools to me. But I think absolutely, I think the intention of your question, yeah, I am saying yes to. Yes.
Does this also work for multivariate polynomials?
Absolutely.
Okay, because I could count every multivariate polynomial that was previous squares.
Good. So the question was, how does this work for multivariate polynomials? In the univariate case, it is true that there is no gap, that if I ask for sums of squares, that every positive univariate polynomial has a sums of squares decomposition, and that is not true in the multivariate case. But the one direction is true. If I can find a sums of squares decomposition, then I'm guaranteed that it's positive. Okay. It's the converse that's not true. And for Lyapunov analysis, we're just trying to find any Lyapunov function that's multivariate, which guarantees that it's greater than or equal to 0, and that's the direction we needed, and that's the direction we have. Good question. So if you can do this, and you can search over parameters, and it's a convex optimization, the implications of that are pretty awesome. Okay. So let me give even just a very sort of simple example of just a global optimization. Let me make sure I've run that. Okay, so this is a famous nonlinear optimization problem, okay? It's called the 6-hump camel. There's a 3-hump camel you might have seen, right? This is the 6-hump variety. Right, so this is just a function of 2 variables. It happens to be a polynomial function of 2 variables, okay? And it has 6 humps, right? So it has local minima. And if you were to ask an optimization algorithm to find the minimum value of that function, you would think that would be a function that has local minima, right? It looks like it has local minima, okay? But because it's a polynomial function, it turns out by changing the form, by writing it instead in this different form, I can find the global minima of that with convex optimization. Okay, and it's using this sums of squares. So the recipe is just I'm minimizing this polynomial function. It just happens to be some polynomial function with interesting coefficients, okay? The way to do it, the way to do an optimization like this, if you want to say what's the minimum over x of p of x, and p of x is a polynomial, that's not quite what we have. We have a sums of squares something's positive workflow, okay? But you could do, for instance, instead, why don't you minimize, or even, let's say, maximize gamma over gamma, okay, subject to p of x minus gamma is a sums of squares. Okay, when I write is a sums of squares, that means I've set it equal to this and added a positive definite constraint. So think about what that is doing. So this is basic. This is similar to saying p of x is greater than or equal to gamma, right? I've just moved it over. I say similar because the sums of squares is not exactly identical to being greater than or equal to 0. It's basically saying that, and then I push up on gamma, maximize gamma. Okay? If I can find some polynomial decomposition of this thing, which has a decision variable here, okay, and since I'm allowed to have decision variables, if I call this thing the polynomial that I want to be sums of squares, and I can solve that with convex optimization, that's pretty good, right? And it gives me the optimal value. It's on the screen there, but it gives me, when I ran that optimization, it says the minimum value is this, and I sampled a million times because it's only in 2 dimensions, and I put out the actual minimum value, and they're basically the same. Okay? It's not guaranteed, so it's not guaranteed to find the minimum value. It's guaranteed to find a lower bound on the minimum value. Okay? But it, in many cases, will solve to the optimal value. You can there's things you can do to check whether you found the true optimum. You can increase the degrees of things, and there's ways to make that actually a real tool for finding the global optimum. But the idea I want to convey is that this is solving something that looks like it should be a non-convex problem by lifting it into this different coordinate system, the decision variables. Right? What are the decision variables for this problem? Just to be clear, what are the decision variables for this problem? Yeah.
Well, gamma, but then also the coefficients you use.
Right. There's a hidden thing when I say is sauce, it adds extra decision variables for that positive definite matrix. So the total decision variables are gamma and p. I've lifted it into a higher dimensional search space by doing that. I've put a strange constraint on this the matrix being positive definite, but the result is in this higher dimensional space, the problem's convex. Does that make sense? Yeah.
I'm curious what the constraint p of x equals to m transpose p of x looks like in the optimization sense. P of x is supposed to be have an enclosed form, right? And then you go, based on what p of x looks like, you would form the matrix, the function basis m of x.
Yes.
Right, and then
That's a good point, by the way. Did you hear what he said? He said, if you give me a p of x, so the code just says p of x is sums of squares. It doesn't ask you for m of x, because for polynomials, we can back out what m of x must be. We can list every possible monomial up to half the degree of the polynomial. We're sure that we have enough, and then we can actually do clever algorithms to chop up and get less of the polynomial, less monomial basis than that. So that's a good step. Okay, I'm sorry, I didn't mean to interrupt you.
yeah, no, actually that's perfect.
That's what you wanted?
Yeah, and then no, actually this is great. Yeah, perfect.
And then I gave a couple of simple examples of like 1 plus 2x or whatever, where the coefficients, in order to make that, once you multiply 1x, x squared times this, then it's just the elements of this matrix must equal, the sum of the elements of these matrix must equal the coefficients that are on the right-hand side. Those are linear constraints. It's just a sum of elements of this. The terms here that contribute to like x squared must match the term here that's like alpha 2. Since they're linear in those and linear in this, it's a linear constraint, which fits in the semi-definite programming formula. Yes?
How could you do p of x minus gamma is a sum of squares? What would that equation look like?
How would I actually write that in the code? Or how do I? Doesn't look quite like that.
Subtracted versus multiplied, I don't see how one could rewrite it as a sum of squares.
Okay, so I'm going to take this thing. Let me call it P2. Okay, that's just now a different. This is just a different polynomial. I've put a gamma into my polynomial, but now I've just got a different polynomial. So really, you could just read this as P2 of x, and P2 of x just happens to be the polynomial generated by this. And when I say P2 of x equals M2 of x, I'll call it G just so I don't have too many P's flying around, right? I'm writing, that's an equals. I'm just writing this in the solver, right? So the left-hand side just happens to be this. One of the decision variables is there. It has to match the coefficients, but it's just only a small generalization on that. Okay, another good question in that, and it goes to what Sava was just asking here is, so does this idea only work for polynomials? That comes up all the time, okay? Like certainly if this is not even in this form, if m is an arbitrary function, then the positive definite combinations of them will still be positive. So this part works for arbitrary functions. The coefficient matching and the ability to just from seeing the left-hand side know what m is, that's the part where we have really good tools from polynomials. And if it was a larger class of functions, that a coefficient matching would be harder. But it's still possible. Like if you wanted to do it for trigonometric functions, you have to do things. We will do things, okay, to make that work. But that's going to work okay. Neural networks, we don't have this working. Arbitrary relooped units and stuff like that. That doesn't work. We don't have. Well, sorry. We do know how to do those matching, but it's combinatorially expensive. Like you have to look at every face of the rectified linear units in high dimensions. And that's some of the ways that people look at verifying neural networks, by the way, is actually very related to that machinery. The other thing that you get from being a polynomial is you get like a whole bunch of algebraic geometry people in your corner, like real mathematicians that like prove every bound about what happens in terms of gaps, and like what happens as p goes to arbitrary degree or whatever, and you get like now you get theoretical computer scientists helping you out, and all these other things that our understanding of that when these things are polynomials is much deeper because of all those connections. Okay. Okay, so this is just a very simple example. Let's do one of the Lyapunov examples again, and I'll do the one that I put up quickly, but make sure we understand it again. So the global stability example from last time was if I have a two-dimensional system, x dot, I'll say is negative x1 minus 2x squared minus x2 minus x1 x2 minus 2x2 to the third power, okay? Just some carefully chosen polynomial dynamical system. And I want to use the sums of squares, convex optimization, semi-definite programming machinery to do Lyapunov analysis of this. Okay, so the first thing I can do is just I can certify if you come to me with a Lyapunov function. Okay, if you were to come and say I think the Lyapunov function is this function, right? I can do the algebra, but actually guaranteeing that it's always negative is hard, potentially. When you get a big complicated function, knowing that it's always negative requires extra machinery. So even certifying the Lyapunov conditions is interesting. Certifying. So if you come to me and say, I happen to know that x1 squared plus 2x2 squared is a Lyapunov function, and I take partial v partial x times x dot, I get some big complicated polynomial function, and I cannot by inspection say, yes, that's negative everywhere. But I can ask the sums of squares machinery, can you find a sums of squares factorization of that polynomial? And that gives us a nice optimization, right? That fits perfectly in this space. It's just a few lines of code, right? So I have my mathematical program. X in this world is not called a decision variable, right? It doesn't, the actual optimization doesn't even know about X. We call them indeterminants. They're the things that have to happen for all X. But if you think carefully about what we said, you'd never actually pass the X to the solver. I'll make sure that's clear in a second, okay? So we say X is the indeterminants, and then I'll say my dynamics are just what I wrote on the board there. That's the X1 dynamics, that's the X2 dynamics. I say I believe that this is a Lyapunov candidate. Okay, I can just use the symbolic tools in Drake in this case to take the derivative. That's partial v partial x, just written as Jacobian with respect to x, times f, with a numpy times, yeah. And I just say I want v dot to be negative v dot to be a sums of squares. That's a polynomial. That's a scalar polynomial function. I can then, this method figures out what m has to be. It creates a symmetric matrix of decision variables. Okay, when I call solve, if it says success, then I do have a Lyapunov candidate. The counter argument is more subtle for the reasons we talked about last time. There could be a polynomial system that doesn't have a polynomial Lyapunov function, all these things, right? Okay, but that's it. That's the.
I was going to ask, how does add sauce constraint know what dimension of basis to use, or is it just optional parameter or something?
There are, so the question was, how does this know what m should be, what the basis of the basis should be? There's a simple answer, which is not what it does, which is you just take the degrees of all the variables and make half of the degree, okay? And then you take all possible combinations of things up to half of the largest degree. Then you will be guaranteed that when you multiply those all together, all of the terms, all of the monomials on your left-hand side will also be on your right-hand side. That would be very inefficient, and not just inefficient because it would be numerically bad, okay? So there's a lot of work that people do, thanks to our algebraic geometry friends, right? To simplify and reduce and remove redundant monomials from that. There's an object called the Newton polytope, which is one of the major heuristics. Someone from my lab, Frank Permenter, who was co-supervised with Pablo, spent a thesis working on facial reduction to make those even better. The choices, to make good choices behind there. But you can do better still. There is a version of this method where you do bring your own basis, because there are problems where if you know additional structure and you can bring your own basis, you can outperform the basic monomial basis. What are the decision variables then in this problem? I heard it, I think. I never said add a new variable, new decision variable. But this step here adds the symmetric matrices, right, in order to make those decision variables. X's, you see the constraint that gets added is actually just the constraint on the quadratic, on the matrix. The solver never learns about X. X are called indeterminants. Indeterminants means for all X in this case. The more interesting case is if I want to search for v. Let's say I didn't know v. Okay, then what I'll do is I'll put a v like this with a bunch of free coefficients, and I'll say that's new additional decision variables, right? Extra decision variables, and I'll say search for a v such that these things are true. Now remember, once I'm allowed to search for v, there could be like, because Lyapunov functions could be super small or super steep up to infinity or whatever, I tend to also say make v be 0 at 0, make v be 1 at some arbitrary point, just to set a scaling. So that's the slightly richer searching for a Lyapunov candidate. Okay, so now I said, same beginning. Now v is not typed in as given. It says make a new sums of squares polynomial. So I just tell it the x. I say that says all powers up to 2. Okay, in these variables. And then this, by saying it's a sums of squares polynomial, it also adds the extra matrix and semi-definite constraint. I say v, where x is substituted at 0, 0, should equal 0. V, where x is substituted at 1, 0, should equal 1, just to set the scaling. And then the other one is the same as before. Yeah? If you solve and succeed, then the decision variables, which are inside V, are the Lyapunov certificate. Yes?
If we have redundant polynomials on our basis, are the SOS representations unique?
If this is redundant, if we were to add things like this, that would be, the math of convex optimization would be fine with that. You would have a whole subspace of coefficients, right? The linear subspace of those redundant coefficients would all be optimal solutions. The solver might be mad at you. In practice, so the set of semi-definite matrices is a cone. Okay, it's called the semi-definite cone. Okay, and it has a geometry that people think about when they're writing solvers and the like. And if your optimal value is on the boundary of the cone, then that's a place where numerical artifacts start to hurt you. So anytime you have coefficients that really should be 0, and it has to figure that out, that's the way so sometimes you'll put solutions on the boundary of this positive semi-definite cone. You just don't want to be like right on the boundary of infeasibility at your solution. For linear programming, quadratic programming, those solvers are so robust that they will take care of it even if you add a bad problem. For semi-definite programming, it's not as strong. Okay, do those examples sort of work? I know I went kind of at length through them, but like if you understand those and you understand sort of, if you feel like you kind of understand what the solver's doing behind the scenes, then you understand the most important ideas. Okay, but what follows is a lot of different ways to use that machinery to ask really rich sets of questions. The most important one, like I said, is to ask a question about regional stability, region of attraction. Right, so right now we've been this is for global stability. You had to find a V that was true everywhere. And the sums of squares machinery is about functions that are for all x. So what if you wanted to say for all x over just some domain, some region of attraction, let's say? How do you ask, right, if you had a friend, let's say an oracle. If you had an oracle friend, and every time you just said, you could walk up to that friend and say, I have a polynomial, and just ask, is this always greater than or equal to 0 for all x? Right? This is like an interview question or something, right? And the friend oracularly, always gives you the true answer. It says true or false, right? What would you ask your friend in order to certify just over a region? Can you change your question a little bit to make your friend more powerful? Or to use your already powerful friend to answer your more interesting question? Okay, so that's our next trick, if you will. I don't want to call it a trick, deep insight. We know how to search over things that are for all x greater than or equal to 0. how do we search over, let's say, for all x inside some domain, p of x greater than or equal to 0. And in particular, I want your friend to say true even if p of x outside this domain might be negative. Okay? I want your friend to still give me, you've got a good, I've satisfied this condition. So we're going to define D again with polynomials, okay? So let's say the region of interest is also described by some polynomial. My claim is that if you can ask this question, p of x plus lambda x g of x is sums of squares. This is potentially a matrix. And lambda x is sums of squares. This is going to be, we'll call this a multiplier polynomial, okay? It turns out that if your friend says yes to this, then I've certified this. Now it's actually not that hard to see, but make sure I got all my signs right. Okay, so my goal is to make this whole thing sums of squares. Okay. What I'm saying is that basically, so the region of interest where I'm trying to certify, g of x is negative, which means having g of x in here is only making it harder for the left-hand side to be sums of squares, especially because lambda is also guaranteed to be positive. Okay, so if I compare it to the p of x, inside the region, this thing is only making it harder to be some positive. So certainly, if this is true, then for all d, p of x is greater than or equal to 0. That side's sort of easy to see, maybe, right? This is only making p of x look more negative. Therefore, if it succeeds in being sums of squares, it must be safely positive in the region. What's interesting is when it's outside the region and g of x is positive, p of x could be negative, and this gets to help you be more positive. Does that make sense? This thing hurts you when you're in the region and helps you when you're out of the region. And if you manage to, with that helper outside and adversary inside, if you will, still be sums of squares, then you've certified that. And you can certify that even when p of x is not globally negative. Yeah?
Is there a significance to the strict and not strict inequalities for p of x and g?
No, I'm being a little sloppy because, no, I think everything has a theorem about related to it. The things we actually can ask the solver tends to be this, and if you want strict equality, you do the epsilon trick. Everything I said is true if those are less than or equal to. Does that idea work? You kind of have to think about it a little bit. This only makes things harder when you're inside the region, makes it easier to be positive outside. Yeah.
So this is like kind of like a Lagrangian like duality kind of idea.
I think the closest analogy is actually to Lagrange multipliers. Think of this as a generalization of Lagrange multipliers where it's actually a whole polynomial. So in fact, what's interesting is the higher the degree you make this, the richer the polynomial you pick for your Lagrange multipliers, the more it can, I mean, I guess what you ultimately want is it to be completely flat, to make this have no impact inside the region, and then completely strong, making this arbitrarily positive outside the region, right? You want lambda x to basically be like, inside the region completely flat at 0, So what we do in practice is we approximate that with lower degree polynomials, and as long as you can certify this, you've certified the conditions. But the proofs about tightness or whatever, you might have to make lambda higher and higher degree in order to satisfy this constraint, that condition. Yeah.
Does rescaling G at all help or hurt like this numerics of that?
I think it can, yeah. Yeah, for sure. For sure. Good? Okay. It's an interesting case. What if I wanted to live on a manifold? Okay. What if D was defined as g of x equal to 0 instead? Okay. This is a related separate case. It turns out the condition you would write is almost exactly the same. You say p of x plus lambda of x, g of x is sums of squares, but now lambda of x is free, is arbitrary. It doesn't have to be positive. And I think understanding this one might even be easier to understand than that, but it has the same intuition. Okay. When g of x equals 0, I'm in the region of interest, and this can't help me. I must be sums of squares on that region. But anywhere where g of x is positive or negative, this can help me make the whole thing positive. Okay? So it's actually a really elegant way to satisfy something to arbitrary precision on the manifold. Yeah, about thinking about it in a higher dimensional space. Okay, that's what we needed. This machinery, you can sort of guess now. I'm going to say this is a region of attraction. I want to certify the Lyapunov conditions, where over some domain. So the simplest example of that is this cubic polynomial that I like. Remember, this was that function that looked like this, where we knew that the region of attraction is between -1 and 1. Okay? The region of attraction of the origin, fixed point. Okay, so the first thing I could do is just say, can I prove that if v of x, there's many ways I could write it, but I'm going to choose to say, let's look at v of x is x squared. That was the example I gave you before. And I want to say that when v of x is less than or equal to 1, I'll actually say I want it to be strictly less in this case, then that implies that v dot of x is less than 0. Okay, so I'll do that using my multiplier idea. This is also, that's famously called the S procedure. It's called the S procedure. One year, someone asked me, why is it called the S procedure? I was like, I don't know. I go ask the experts. And one of the experts is Sasha Magretsky, who's a Russian mathematician in our department. And he says, it was invented by Russians, but there's no S in the Russian alphabet, so I don't know where it came from. So I then that's what, and then but I found somebody who's written a whole paper about where S came from, and I linked it in the notes. So, but I can't. There's not a short answer. It's confusing. S procedure. Okay. So do you see how this query, if I could certify this query, I could prove the region of attraction of that? V of x less than 0 is exactly a way to specify that domain, right? And if this plus this, so what I'm going to do is I'm going to make a multiplier, and I'm going to ask that v dot of x, negative v dot of x, plus lambda of x. I always have to make sure I get the signs right. V of x minus 1 is SOS. See if I got that right. I wrote it differently, of course, there. And then lambda x is SOS. Okay. And more generally, if I didn't know that 1 was the answer, I could write this as v of x minus rho, okay? But I'm setting rho equal to 1 right here first. And then it's just really a very simple mathematical program to write. I say f is x dot, or negative x plus x cubed. Compute my v dot. I set rho equal to 1. I make a lambda and say that it's a polynomial up to degree 2. That's a sum of squares. And then I ask for this thing to be sums of squares. What are the decision variables in this problem? Vars, variables. Okay, those are the decision variables. Unfortunately, they're named the same. Okay, there's two polynomial matrices, right? Because there's two sums of squares constraints, one for lambda and one for v dot. The semi-definite, the matrix, G or whatever I've been calling it, is called S here, but it's the matrix that it was built, is called S. It has decision variables S00, S10, S11. There's actually 3 of them, right? There's 3 sums of squares constraints, I guess. I put the V. There's this one. There's this one. Where's the red? I should have named them better. Oh, that's the same. It just was printed in a weird order. But the 1, 1 is also there, and the 2, 1. Yeah, it's just two big S matrices. Yeah, one of them is 2 by 2, and one of them is 1 by 1. Right? Yeah. This one, the second one starts here and goes to here. Okay. Those are the decision variables. And when it succeeds, it says yes, x squared less than 1 is in the region of attraction. Why did I write the domain like this? Why didn't I write something else like, x between 1 and 1, negative 1 and 1? Remember that the region of attraction conditions, what are you going to say? Yeah?
Because the domain is defined by g of x is less than or equal to 0.
That's true. That's correct. But why did I use the Lyapunov function to write the domain? I could have written it as I don't know, x to the 4th less than 1 or something unrelated. Remember, the conditions for a region of attraction are that you have to be an invariant set in addition to being a region. So if I certified over some region in space that the thing was v dot, that would not say it's a region of attraction yet. I also have to show that that set is an invariant set. So the choices of domains for region of attraction are almost always sub-level sets of V. because then they're self-consistent. Once I'm inside V and I've certified the conditions inside the V, I won't leave V. So that means this region's also an invariant set, and I get both of them all for same price. Okay? If I didn't know, go ahead, yeah?
So, but, for example, if you had two different Lyapunov functions, you could define an invariant set with one and then try to certify it with the other.
That's true. You could. He says
That's
if you have
a good idea.
two different Lyapunov functions. No, we actually do. There are cases where you try to certify conditions over different regions, but to make a region of attraction analysis, you need it to be an invariant set. If you can get an invariant set some other way, you're welcome to. Sage.
Yeah, and then just to make sure that I'm getting the S procedure right, I could trade the v dot x and the vx minus 1 in the sauce condition, and that still would give me like the same answer?
Awesome question. Okay, he says, I could have, so I want to, you got to be a little careful. The implication here is one-sided. I say whenever I'm in this,
Yeah.
I want to be here, so I could not have just put this there. But it turns out this is the game we start playing, okay? So there's all these things that we wanted to compute. We want to compute regions of attraction of like piecewise continuous systems, or we want systems that have saturations, or we want things that, and the games are finding different ways to write this. And one of them is, as you say, is finding a way to write it the other way and put the multipliers here, okay? Why is that? So, okay, so let me just say for a second, I'll get there in 2 steps here. So if I put a row here, okay, and right now I set rho equal to 1 as a constant, and I solve the problem. And it said pass. You pass. If I wanted to search for the region of attraction, one of the things I could do is I could just solve this many times. Rho is a scalar. So if I pick a very small value, as long as it's locally stable, I would expect it to eventually pass for a very small value. Okay, and then if I start increasing rho, it will eventually fail. Turns out there's a nice monotonicity property there that you can actually just do golden selection, branching search in order to find that, okay? So you can do a line search to find the biggest rho to find your region of attraction. But that's slightly unsatisfying. Why didn't I search for rho, optimize rho? Okay, and this is to Seiji's question. So the problem is that if this is a decision variable, the coefficients of this are also a decision variable. And if I multiply those two together, then it's no longer a linear constraint. Okay? So you think to yourself, okay, well, I don't want that bilinear equation. So I said that quickly, but why is that bad? So if I get, remember I said any constraint that I could fit into like ax less than or equal to b is a good convex constraint. If I got x1 times x2 equals b, that's a bad non-convex constraint. When this happens, I'm getting one decision variable times other decision variables, which is a non-convex constraint. I can't use my convex optimization tools. So wearing this hat of like trying to find convex formulations, you think, wouldn't it be great if I could put the multiplier over here? Okay, and you can, but the implication is a little different. So what you end up saying is that when v dot of x equals 0, well, let me write it first and then we'll say it, then either v of x is less than rho, or sorry, is greater than rho, or v of x, or x equals 0. Make sure I'm pretty sure that's right, yep. Okay, so this is the picture I want you to have, okay? So I'm in 2D now, x1 and x2. Let's say I have a region of attraction here I'm trying to certify, okay? If I were to plot the places where v dot starts going uphill, where it has to be downhill, I'm going downhill in here, my v dot is negative, okay? Out here, maybe I'm going somewhere else. Somewhere there's a transition, there's a boundary where v stops going downhill, starts going uphill, okay? If I can say if the boundary here is outside that region, and I know that I'm locally stable, you have to check that condition separately, but that's an easy thing to check, then you can also certify the region of attraction. And writing this puts the Lagrange multiplier on the V dot term and is jointly convex, and you can search for rho. Now that's a detail that we're actually, the van der Pol oscillator problem that you're going to do on your problem set will step you through that version too. Okay, so I hope you'll understand the details of that. But the game that you'll be slowly learning as you do more of these is trying to find ways to write the conditions that certify something about the dynamics in a way that is compatible with your convex optimization toolbox. Okay, and that turns out to be a particularly nice one for a region of attraction where you know V, but you don't know rho. Okay. Good. Yes.
It feels like you're cheating.
Oh.
That you have. Like
That's
you
good.
propose a V and you try. You see how much can you certify with this V,
Okay.
right? It seems to me that finding Lyapunov functions is hard.
Okay, that's a good question. Am I cheating? Isn't finding V the hard part? So here's one example that I'll show you at the end, but what if you do LQR at the top, around a fixed point? The cost to go from the LQR is a pretty good Lyapunov candidate, and you just want to find the largest level set of the candidate you got from LQR that works for the nonlinear system. That turns out to be exactly this formulation. You bring a cost to go function from your synthesis, and all you want to find is when can I trust that, right? And for instance, there you guys are, for Kyle, if you want to certify when to switch from the energy pumping to the upright, remember we said that the energy shaping doesn't actually stabilize the upright, you have to switch to LQR. You could do that to compute the region of attraction of the LQR at the top and know exactly when to switch. Okay, you take your stretch real quick, and then we'll do the next examples. Everybody says they like that, but I rarely, I get too excited. I forget to do it. Yeah, go ahead.
Just a general question. The V dot doesn't have to be some squares. That's why we're adding like the lambda and everything. But some squares makes it easier to solve.
Good question. So let's bring it back. Yeah, good. So you said V dot of x. So what I'm worried about is for a system, let's take the example of balancing an acrobat at the top. I compute an LQR controller. I know it's going to work around the linearization, but if it gets too far, it's going to fall down. So asking for that cost to go to be a Lyapunov function for globally is not going to work. I want to be able to, V dot is going to be increasing in some places. I want to say that at least in some invariant sublevel set, V dot is going downhill. That would give me a region of attraction. So that's why you have to do this multiplier trick. Say V dot only must be less than 0 inside this region. Good? Okay, so let's just imagine sort of what you can do about it. Remember, we talked about the robust stability. Remember, we said for the Lyapunov, for the linear Lyapunov, it's a semi-definite program. You could have just checked the eigenvalues, but I showed you a semi-definite program. But the power was you could even do robust stability, right? So what about for the for the cubic example? Same thing, right? We now have this extra power of doing robust analysis if we want. So I just put a couple examples together of like, what if it's, normally it was just negative x plus x cubed. What if it's like delta times x cubed and I don't know what delta is, okay? So let's just even think about what the curves look like. That means I don't really know, like, it could be that curve, it could be that curve, it could be that curve, it could be that curve. But if you find a common Lyapunov function that works for all delta in that region, which you can do with another S procedure. You can have a delta be an indeterminate and put another S procedure to say for all delta, for all x into some region, then you can find the robust region of attraction, right, with the sums of squares program. It's interesting. So what about this one? So additive uncertainty. This is a standard thing. Yeah, that's what it's going to do, right? So if I don't know what that addition is, then it's going to give me curves like this. So if I ask for it to find a region of attraction to the origin, what's it going to say? Yeah, it's going to say there's no region of attraction. I can't find you a region of attraction to the origin because depending on the parameter, the fixed point moves. Okay, but you can actually check different conditions. Where's the fixed point? You can check different conditions just saying, if instead of saying for all Vx less than rho, I said when V of x equals rho, V dot is less than 0. Let me write that since right? What we said before was V of x less than or equal to rho implies that V dot of x less than 0. But if I relaxed my conditions to say V dot of x equals rho, or V of x equals rho implies V dot of x less than 0, then that's kind of like this picture here. What I'm saying is at least on the boundaries I'm going in. I'm not saying that I'm going all the way to the origin. I'm just saying it's an invariant set. Every time I get to V of x less than rho, I know I'm pointing in. And you can find like the largest invariant set for a set even if you don't know where the fixed point is. Or if people have seen, Jean-Jacques has done a lot of work on contraction analysis and contraction theory. That is also a way to think about finding a stability proof without knowing where the fixed point is. I'll mention that more carefully in the next lecture. Okay, that's a powerful toolbox now, right? It's not just one polynomial system, but we can do robustness analysis inside it. Okay, let's get away from a one-dimensional example. Let's do a two-dimensional example. I mean, it works for higher dimensional, but the pictures are better in low dimensions. Okay, so this is a classic nonlinear system. It's called the van der Pol oscillator. And you're going to run through an exercise on the homework to do this. Okay, so it happens to be a second-order dynamical system. So this is a phase portrait, theta versus theta dot. I should label my axes. Okay. And it happens to be an oscillator, right? So if I plot the vector field, it's always going around in the phase portrait, clockwise. But it happens that there's a fixed point at the origin, but then everything else goes out until it comes and goes into this stable limit cycle. We'll actually study this again when we talk about limit cycles for walking robots and the like, okay? But it turns out the dynamics of this will converge to that black orbit. And from the outside, it actually converges in. It's a stable nonlinear oscillator. It turns out to be a great example for region of attraction analysis because, well, this one, what's the region of attraction? It's just the point, or you have to think about region of attraction of a limit cycle, which we will do. But what I'm going to do right now is I'm going to reverse time. Okay, so we're not going to study this time the van der Pol oscillator. We'll look at the time-reversed van der Pol oscillator, which has the interpretation of changing the direction of those vectors. Okay, so now it flips the stability. If you just put a negative sign in front of that, it flips the stability. And in fact, the known limit cycle of the forward dynamics becomes the known boundary of the region of attraction of a fixed point that's now stable at the origin. So it's like a really cool example where there's a very non-trivial region of attraction, but we can kind of find it. Okay? And doing the sums of squares machinery and what you will work to on the problem set, you can search over Lyapunov functions that will find pretty big regions of attraction. Okay, so the red is the true region of attraction. This is the estimated one. This is the sublevel set of a quartic Lyapunov function. So degree 4. Yeah, it's pretty good. The conditions that we write with these S procedure are designed to be conservative, right? So if we're in the game of trying to prove stability over some region, we want to always fail on the inside. So the certification, if we get one, if we pass our test, we'll have a proof that at least the purple region, I don't know how I get that sort of strange color, but purple region is inside the region of attraction. We don't have to worry about possibly being outside. It turns out the problem's easier if you allow yourself to have outer approximations. You can do more things in a convex way, but we normally try to worry about conservative being on the inside. Okay. Now, the true region of attraction is not a convex set. So how do I know if a set is convex, right? So if I take any 2 points in the set and draw a straight line between them, if the set is convex, I need all of the points between any two of those 2 points to be inside the set. And just my little cursor proof here is that I've picked those 2 points, and there's some elements that are outside the true region of attraction. So this is a question. So does that matter? Does that mean sums of squares, our convex optimization is only going to be able to find the best convex inner approximation? Depends on your basis functions, right? So we've moved this into a higher dimensional space, and the shape in this space doesn't actually matter. So as a fun example of that, we can construct another interesting known region of attraction. We make a vector field so that the orange is the known region of attraction. And then we search for up to degree 4 polynomials that are the biggest, proof, the biggest quartic sublevel set that we can prove is inside the true region of attraction, and we get the yellow. Okay, so the thing we estimated is not convex.
Assuming no issues with like numerics or computation, as the degree tends to infinity, do we expect that the optimal region of attraction with respect to that basis approaches the truth?
That's a great question. So he says, if barring computational numerical issues or scaling issues, would we expect that to converge? If I increase the degree of the polynomial inside, would it converge to the true region of attraction? The gaps do exist, right? So I think the fact that not all polynomials are not all positive polynomials are sums of squares, not all Lyapunov polynomial systems have polynomial Lyapunov functions. Those are the kind of things that are going to fight you at the boundaries. But I think in practice you'll get closer and closer and closer. I think that, there's. Yes, I know that gaps exist, but I suspect it will work very well. I think we cannot say that it will converge. Okay, and then the real application, right, for robotics, I think a great example, for instance, is to do LQR. Okay, this is LQR on the quadrotor, like I showed you before. It's stable. And then you ask, what is the region of attraction of the linear controller on the nonlinear system? Remember, I drew vector fields and said linearization is pretty good for a pretty big space, but how do you know which space it's good for? Well, now we have a tool, right? And for quadrotor, this is in 12 variables, right? No, this one's only 6 variables. Sorry, it's more. We can do the 3D quadrotor fine too. Okay, but I can't. This is a slice now through the true region of attraction because that's a 6-dimensional object, the sublevel sets. Okay, and really the only thing to note here is that it's big. I guess it's like it found a pretty big region of attraction. Okay, and there's 2 versions of it here because I also did one with like mass unknown, just to show that you can do the robust uncertainty on these problems too. Okay, so you could do a linearized controller and then ask how well does that linearized controller work for the nonlinear system. Yeah.
Sorry, are those radians?
This is radians and this is radians per second. Yeah. It's too small, you think?
Yeah, well, just like a tenth of a radian is like 10, 15
yeah, it's okay. So the true region is much, much bigger. Yeah. And this is also like a much higher dimensional object. You're gonna rain on my parade on like that?
I wasn't gonna rain on you for that. Stop.
Come on, that's that's big, man. That's big. No, we could do better. I'm sure we could do better with like higher degrees and stuff like that. Okay, questions up to that? Does that machinery kind of make sense? Let's see if anybody else has a question. Does that machinery kind of make sense? Yeah. There's a lot of variants of how you can write this to ask different questions. I actually have, I was remaking my whole list this morning of like all the permutations, and I will have the notes converge to like list all the details, but they're all minor variations of this. You know, how do you do it with inequality, with saturations in your actuators if you have a closed loop system, and how do you do implicit dynamics, and how do you do all these different things, okay? There's one really big one that I want to finish with, but again, I'll pause with any questions. Okay. All right, the big one. Are you good? Do you want to ask a question?
I have a question, but it can wait.
You can ask.
So we've been handling uncertainty in the dynamics where like there's some fixed dynamics and we don't know the parameters.
Yep.
Can we also deal with dynamics where there's like some stochasticity? Like can the quadrotor balance if there's wind and we don't know what the wind looks like?
So the question was, what about stochasticity? So there's different ways to treat robustness. What I've been showing so far with the S procedure naturally handles worst case uncertainty. You could still have a distribution inside that, but you're going to take the bounds of that distribution. You want it to have finite support, and anywhere inside that, you would do a worst case analysis. If you wanted to do a stochastic analysis, then you would be asking a slightly different question. You'd say like, I want to converge with some probability, for instance, and then I got to add that to my list of things to include. There's versions of this where you, instead of searching for a Lyapunov function, you search for a martingale. Basically, you find you say that something goes downhill with probability, in expectation. Basically, it goes downhill, and you can put bounds on the probability of leaving a region. So yes, you can handle that kind of stuff. Big question that you're all, on the edge of your seats worrying about is that robots aren't polynomial, right? Like, what the hell? You've been talking for a whole hour about polynomials equations, and robots have sines and cosines in them, right? So what are we going to do about that? So let me land that idea to finish up. There's a simple answer, which is you can approximate any smooth nonlinear system with a Taylor approximation, which would be a polynomial approximation. That's cool. You can do that, but it's more elegant than that. Okay, because you can even do that and then bound the errors of your Taylor approximation and use worst case analysis to certify that even your approximated solution is a good model of your nonlinear. That is one path you could take. But let's take a different path here. And just face up to that fact, okay? They're rational polynomial, okay? But they're almost polynomial. Still not convinced, right? So I've been writing stuff like this. Right? That doesn't look very polynomial. What the heck? But it turns out the way that nonlinearities enter the equations is the sines and cosines, for instance, enter the equations is very special. They're trigonometric polynomials, okay? In particular, I'll never get like sine of m theta, for instance, okay? And Yeah, these things turn out to be only multilinear trigonometric functions. I get sine of theta 1 times sine of theta 2, I get cosine whatever, but I don't get weird things on the inside of the nonlinearities. And the reason that's not an accident, that has to be that, because what rigid body means is basically a distance preserving constraint, right? What a rigid body dynamics is fundamentally governed by the constraints that saying, any 2 points on that body, if I pick 2 points, like the distance between those points is some constant. That's the definition of a rigid body. Sine and cosine is one way to write that, okay? But fundamentally, the rigid body kinematics and ultimately dynamics have this kind of form. You just have to expose it. And the simplest way to expose it is I'm going to just go through all my functions. Every time I see a sine, I'm just going to call that s. Okay, every time I see a c, a cosine theta, I'm just going to turn that into a c. I've got theta 1, I'll make s1, c1, like this. And my claim is that the equations will be polynomial in s1 and c1. And I want to live on a domain where s squared plus c squared equals 1, which is the same as sort of saying that, okay? But I know how to use the S procedure to handle that, okay? So if I just make a substitution everywhere and change my sine thetas and cosine thetas into S1 and C1, then I'll have a polynomial dynamical system in this form. And I can certify it over a domain. You can do a region of attraction, but always you want to only worry about satisfying that when s squared plus c squared equals 1. Okay? Now this, I said rational polynomial. Okay, so in this case it's just polynomial in the single degree of freedom. But in general, right, I have mq, q double dot, plus cq, q dot. Something like this. M is going to turn out to be polynomial in sines, cosines, and theta dots. Okay, well, actually, not even theta dot, just in sines and cosines. C is going to be this whole thing is going to be polynomial in sine, cosine, and theta dot. Similarly, all through, okay? But if I take the mass matrix inverse to get the forward dynamics, the mass matrix inverse is going to turn it from a polynomial equation into a rational polynomial equation. Okay, so the more elegant approaches in the sums of squares certification, which we're still doing research on today actually, is to just operate with the equations directly in this implicit form. Okay, you can try to do the Lyapunov analysis without taking a mass matrix inverse. Just working directly on these equations. And that's in general, there's general strategies for doing rational polynomial. Okay, but when I showed you the global analysis of the pendulum, finding with sums of squares the true energy, mechanical energy, I was doing this and this. You can look at the code, it's right there for you. Okay, and I was finding the best Lyapunov function, and I came up with mechanical energy. So you can actually operate directly on those sines and cosines like that. It is polynomial, as long as you avoid mass matrix inverse.
If the system were fully actuated, could you sort of undo the mass matrix inverse with your controls and make it a
That's a deep question, but so the question was, if the system was fully actuated, could I invert, or could I replace the mass matrix inverse? Yes, you could, but that's actually the hardest thing to invert with control. Like people tend to not do that. When we talk even about, in the manipulation class, we talk about impedance control versus stiffness control. People actually don't tend to do impedance control because reshaping the inertial matrix, I just did Panville-Wave paradox. When we reshape the mass matrix, that's hard. See my chalk skipped? That's like a classic contact mechanics thing. I can't even do it, but I had a contact instability. Oh well. It's like, I wish I could do that on demand, but it's cool. Like Walter, yeah, anyways. Good. So I think we understand a lot of what I wanted to get through. Like I said, there's lots of variations. I actually have my to-do list here, like all the things. I was like going to write it all down. I thought, yeah, I'm just going to show them my to-do list and show that I'm working on it. But you know, from implicit dynamics and trig poly substitutions, and we have better ways to solve the SOS problems. We have outer approximations. We even know how to do Lyapunov through contact, which we'll get back to later. Good. Okay. See you Tuesday.